Okay, so this last question 6 that we're going to walk through, it's an interesting substitution problem, and I even question whether or not to include it here. But given that it's a unique problem that I've never seen on the HSC, it's actually a good one to challenge your application of substitution. And that it's telling you that we're using this substitution that x is tan of theta. So we think about what substitution means. It means that anywhere I see x or dx, I need to replace it in terms of theta or d theta. So following the same process for u substitution, find the derivative of x. So that's dx d theta, because the right hand side is in terms of theta. So the derivative of tan is secant squared theta. That needs to be rearranged because eventually I'll be replacing the dx in my original integrand. That dx is secant squared theta d theta. So if I follow the process for substitution, since x is now tan of theta, replace x and square it. So 1 plus x squared is now tan squared theta to the power of 3/2, and then dx is now secant squared d theta. So regardless of that kind of interesting, unique way to apply substitution that doesn't really quite fit examples that you've seen prior to this also challenges integrating where you need to remember your trig identities. That you're probably looking at your denominator now and thinking, oh, I'm pretty sure that that's a Pythagorean identity, that it's secant squared theta to the power of 3/2 still times secant squared theta. Oops, I missed that theta up above. Let me correct that. So and if you remember your power rules again, so when we simplify that secant squared to the power of 3/2, I won't skip a step here, that becomes secant cubed theta, still times secant squared theta out back. And this was a step that I didn't skip. If I go and then simplify this multiplication of the fraction times secant squared, that actually simplifies into 1 on secant theta. And this is actually quite a beautiful problem in that really what we end up integrating once we perform all those trig identity manipulations, we're actually just simply integrating cosine of theta, which is in and of itself really easy. That's sine of theta. And again, with all that work, you feel like, oh, well, I'm done. Slap the plus c on there and I'm done. But remember from the beginning that x is tan of theta. And I cannot leave my final answer in terms of theta. So I need to actually solve that substitution that I started with for theta. So that's where that inverse tan of x comes into play. And that's what's going to replace the theta. So I'm actually looking at the sine of the inverse tan of x. And again, some people may think that they're done. And I would suggest, let's extend yourself. Let's go a little bit further. Let's finish this off, especially if this happened to be a multiple choice. I can guarantee that that would not be one of the choices, because really what you've got here is, since it's an inverse tan, and it would apply even if it was an inverse sine or an inverse cosine, it's actually a ratio. And a ratio that corresponds with a right triangle, where if I call this my x, the opposite, I don't want to call that x. That's confusing. Let's call it alpha. Not to call it theta and confuse it, but my opposite side of that is x. My adjacent side of that angle is 1. So by the Pythagorean theorem, x squared plus 1 squared, the square root of that is my hypotenuse. So since I'm actually finding the sine of the inverse tan of x on 1, I'm actually looking for the ratio of sine, which is now the opposite of that angle that I called alpha, which is x on my hypotenuse, which is x squared plus 1, square root of that, plus c. And that is your final answer. And again, if this was a multiple choice, I can guarantee that that would be one of the choices and not the sine of the inverse tan of x.